The best way to learn how to use Lagrange multipliers is to do a ton of examples, so let's do another one. Let's find the extreme values of the function x squared y when x squared plus 2y squared is less than or equal to 6. As usual, to start off, I'm going to draw a picture of the space on which we'll be working. The boundary looks like an ellipse, but notably, since x squared plus 2y squared is less than or equal to 6, this means that we're also working on the interior. Let's tackle the interior first, for which we must find and classify the critical points of the function f. Taking the gradient and setting it equal to 0 gives us the following two equations, which we have to solve for x and y. Now, equation 2 tells us that x is equal to 0, but if we plug that into equation 1, we get 0 is equal to 0. This means that both equations are satisfied for any value of y. Well, not quite any value, since we still have to live in the interior of the ellipse above, so plugging x equals 0 into the constraint tells us that y is between plus or minus root 3. Thus, the set of all critical points looks like this. So we have to classify all of these, and of course you're free to try and use the second derivative test if you like. However, it turns out that this is not at all necessary. The value of f on this set works out to just give 0. But it's easy to find points nearby which are both bigger than 0 and which are also less than 0. Thus, nothing in this set has the potential to be an extremum. If the max and min exist, they must therefore occur on the boundary corresponding to x squared plus 2y squared is equal to 6. The function g, which describes the boundary, is x squared plus 2y squared minus 6. Differentiating to find the gradient gives 2x 4y. So invoking Lagrange multipliers, there's some number lambda such that the gradient of f is equal to lambda times the gradient of g. Setting these to be equal gives us two nonlinear equations, which we can simplify as follows. Together with the constraint function, we have to solve this system for x and y. I'm going to start by rearranging equation 3 as so. And from this, we can conclude that either x is equal to 0 or y is equal to lambda. Assuming that x is 0, we can plug this into equation 4 to get that 4 lambda y is equal to 0, so that y is either 0 or lambda is 0. So if y is also 0, and we plug that into our constraint function, we get that 6 is equal to 0, which is of course nonsense, causing us to reject this case. If lambda is 0, then both equations 3 and 4 are satisfied for any value of y. So plugging x equals 0 into the constraint tells us that y is equal to plus or minus root 3. So our solutions are 0 and plus or minus root 3. But this is really starting to look and feel a lot like what we did with the interior points. And by precisely the same sort of argument that we used there, we'll be able to argue that these 2 points don't have a chance of being extrema. So x equals 0 didn't give us any useful information, and we turn our attention then to the case where y is equal to lambda. If we plug this into 4, that gives us that x squared is equal to 4y squared. We then plug that into the constraint, which gives us that 6 is 6y squared, from which y is plus or minus 1. We then have to find the corresponding x values, and if we do that, x is plus or minus 2. Thus, there are 4 candidates, one corresponding to each choice of sign in x and y. Since we don't have a second derivative test on the boundary, we just plug these back into our function f. And we'll exploit the fact that the x squared term here doesn't change sign to make our computations a bit easier. Thus, plus or minus 2, 1 are the global maxima, while plus or minus 2, negative 1 are the global minima. Now it turns out that we're done, but a natural question to ask is, if we had started with equation 4 instead, would we have found any additional cases? Turns out the answer is no, but I'm going to leave it as an exercise for you to check that no new additional cases appear.